Okay, welcome back to number theory. Today we're talking about polynomials. First, let us define what a polynomial is. So for a ring R, the polynomial ring is going to consist of elements which are formal sums, where each coefficient lives in the ring R. And this is a ring where if we take two formal sums, two of these sums, bi x to the I, then the sum of them is just going to be ai plus bi x to the I, and if we take a product of them, or I'll use j here, so I goes from 0 to n, j goes from 0 to m. Here, this is just going to be a sum of ck x to the k, where k goes from 0 to n plus m, where ck is defined to be the sum of ai b k minus I, where I goes from 0 to k. So, as an example, we know how polynomials work. Say I have x squared plus 1. If I want to add this to, say, 2x squared plus 2x, well, this will equal 3x squared plus 2x plus 1. And if I want to multiply these two together, I'm going to get 2x to the 4 plus 2x squared plus 2x cubed plus 2x. Yes. And the way I got this is, if you look x squared and x squared, that's the only way we can get a 4, and so that's 2x to the 4. X and x squared, that gives us the x cubed term, so I guess this should be cubed and that should be squared if we're writing it in decreasing order. And then to get the x term, you do that, and this gives the x squared term. So that's how you can define polynomials. And the degree of a polynomial is the largest non-zero coefficient, or the index of. So, for example, the degree of x squared plus 1 is 2, because x squared is the leading term. But if I take, say, 3x cubed, this degree is 3. And if I take, say, the degree of 1, well, this will be 0, because we can think of 1 as this is the degree of 1 times x to the 0, because anything to the 0 is 1. But we're going to define, this is not defined, or some people will define this as negative infinity. So this is kind of what polynomials are and what the degree is. So first, let's prove the following statement. If we have two polynomials, then we're going to have the degree of f plus g is less than or equal to the maximum of the degree of f and the degree of g. And kind of a proof of this is, well, say f is the sum of ai x to the I, and g is the sum of bj x to the j. And here I have two different indices, so this one goes up to n and this one goes up to n. And let's just say m is less than or equal to n. Then the leading term of f plus g is, and here I'm thinking an is not 0, and here bm is not 0. So f has degree n, g has degree m. The leading term of f plus g is going to be an, but it could possibly be bm if n is equal to m, and otherwise it'll be an if n is not equal to m. If n is not equal to m, we know an is not 0, so this would imply that the degree of f plus g is n, which is less than or equal to the max. But in this case here, if they are equal, if bm is, or I guess here, I'll call it bn is minus an, this tells us that we go down a degree. And so the largest term has to be strictly less than. So for example, if I have x squared plus 1 and I am adding negative x squared plus x, this is x plus 1. So the degree just went down by 1. Furthermore, so that's what happens when we add. When we multiply, if I have two elements here, then the degree of f times g is going to be less than or equal to the degree of f plus the degree of g. And it is an equality if one of the leading coefficients is not a zero divisor. So a way we can prove this is just look at the formula for Cn. So if we look at the formula that defined the multiplication, we're going from k equals 0 to n plus m. Well, if we look at this, if we go for n plus m, well, the only non-zero term is going to be a n times bm, right? So that's going to be the leading coefficient. That's the only way this sum is k. And I guess what we're saying is if this index here is not, it's 0 if it's not in the right range. So the only way this with non-zero coefficients here is going to reach n plus m is going to be an times bm. Thus, we're going to have am times bn, or an times bm, but what could go wrong is if we have a zero divisor. So if we have, say, ai x to the I and bj x to the j, then the largest coefficient we see, coefficient of x to the n plus m is an times bm. So the degree of f plus, or f times g, is equal to n plus n, which is the degree of f plus the degree of g, as long as an times bm is not 0. Namely, if leading coefficients are not 0 divisors, then you kind of get this nice equality here. And so kind of a corollary is for fields, the degree of f times g is the degree of f plus the degree of g. So now let us do the following. We have a division algorithm. If K is a field, I have f and g are polynomials. Then there exist polynomials q of x and r of x, such that the degree, or such that f of x is q of x, g of x, like q of x, g of x, plus r of x, where the degree, well, I guess r of x could be 0, or the degree of r of x is strictly less than the degree of g of x. I guess if you take the 0 polynomials, this is why we can consider it to have negative infinity, because these kind of inequalities and everything will hold. So kind of here's the proof. So what we could do is we note if the degree of f is smaller than the degree of g, then q of x equals 0 and r of x equals f works. So let us assume that the degree of f is greater than or equal to the degree of g. So what we can do now is we can say, all right, consider the set x of, how do I want to do this? So I want to consider a set of elements the degrees of f minus gq such that q is a polynomial over the field. And let's don't include negative infinity. So if g divides f, we are done, since this would give us an r of x equal to 0. So assume g does not divide f. So that is, this polynomial here can never be the zero polynomial. So the first claim, well, we note x is not the empty set. Because just take q equal to 0, right? And the degree of f is assumed to be positive, and we're done. Oh, I probably... We probably should specify here that g is not the zero polynomial. So we know that some degree exists. So by the well-ordering principle, we have there exists a smallest degree. But here, I kind of want to make sure that the smallest degree is, because that's how I'm going to cook up our R of X. I claim that there exists some Q where F minus GQ, or the degree of F minus G times Q, well, I want this, the degree of this polynomial, to be smaller than, because this will be our R, we want this to be smaller than the degree of G. So let's cook up a Q. First, we note, if we write F as kind of a sum of AI x to the I from 0 to n, and G is a sum of bj x to the j. So what we can do is we're going to cook up Q recursively. Let Q1 equal, well, since we're in a field, we're going to make it be negative an over bm x to the n minus m. And recall, n is greater than m. So what we're doing here is, if we consider q1 of x, this is going to look something along the lines of, well, negative an over bm x to the n, well, there's an n minus m and an m, plus lower order terms, right? So what we just cooked up is we showed that, well, f minus q1 of x times g, well, the degree of this, so the degree of this is less than n. We want it to be less than n. So now what we could do is we can continue to cook up this element. So basically we induct. So here we can find, so this is a polynomial. And it might look something like I equals 0 to n minus 1 of ai x to the I. Or maybe I shouldn't use a here. Maybe let's use c. And then if we let, now if we consider f minus q1 of x g minus, so if we want to kill off this largest term here, we can do, what do? We want to do ci over bm x to the n minus 1 minus m. If we do this times g of x, well, this here is going to kill off the highest order term here, and then the degree of this thing is less than n minus 1. And then we're just inducting, and then until we get the degree. And I should note here that, or not clone, I want to, we can factor out this g of x here. So this is a q1 of x minus ci over bm x to the n minus 1 minus m. And this here is what we'll call q2 of x. And this is f minus that. So the degree of this is less than n minus 1. And basically, we're going to continue, and we're going to induct until the degree of f minus q is strictly less than m. Q times g. And that tells us that we can find such a polynomial. So this is the division algorithm for polynomials over a field, and I should note this doesn't hold in general over an arbitrary ring. So something else we can get out of this is, so a root of a polynomial, f of x, is some element, let's call it a in R, such that f of a is 0. And what I mean by f of a here is we plug in the value of a. So what we can do now is, using this division algorithm, we can say in a field K, a is a root, maybe a and k, is a root if and only if x minus a divides f of some polynomial f. And so a proof of this is, well, we have the forward direction. So if we have a root, then let's use the division algorithm. Then we have that f of x is x minus a times something plus r of x. So this is some q of x. Now let's plug in a. If we plug in a, we get that f of a is a minus a times q of a plus r of a. So that's just r of a. And since we're a root, so that we have, so since we're a root, this tells us that r of a is 0. But the degree of r of a is less than 1. So this tells us r of a is constant. So f of a is x minus a times some q of x. So in a field, we have, if we're a root, then x minus a divides our polynomial. In kind of the opposite direction, if x minus a divides f, well, this just means that f of x is x minus a times some g of x, but then f of a is a minus a times g of a, which is clearly 0, so a is a root. So, as a corollary of this, if I have some polynomial f in a field, this has at most, the degree of f roots. And kind of the way you see this is if you have a root, you factor it out, you decrease the degree by 1, and you can only, each time you factor it out, you only get that many roots. So, why did I want to talk about all of this? It's because I wanted to prove the following theorem, called Wilson's theorem. And this says, if p is prime, p minus 1 factorial is equivalent to negative 1 modulo p. So we're going to prove this. And the way we're going to prove this is the following. We're going to note that if we look at the polynomial x squared minus 1, this we're going to think of as a polynomial in z mod pz, which we showed was a field, I believe, 2 lectures ago. This has at most 2 roots, namely plus and minus 1. So, plus and minus 1 are the only roots of this element. Note, so what this tells me, now we're going to use the fact that z mod pz star is a group. So every element has an inverse. And namely, it's a group, and it has size p minus 1. So every element has an inverse, and the above shows that only plus and minus 1 are their own inverses. So what we can do now is we can say, well, we know plus and minus 1 are their own inverses. So if we multiply together every element, so we know that this is going to look like 1, 2, 3, all the way to p minus 1. Well, if we pair each element except for 1 and minus 1 with its inverse, what's going to happen is, well, the product of an element and its inverse is 1. So when we take the product over everything in z mod pz star of x, which is p minus 1 factorial, this is going to be equivalent to, well, just pairing up the x with the x inverse, that's going to leave us with 1. So it's going to be 1 times p minus 1, which is equivalent to negative 1 modulo p. So this is how you can go ahead and prove Wilson's theorem. And note, one of the key observations that we needed was, well, this x squared minus 1 has exactly 2 roots, and we had to use the fact that z mod pz is a field to do this. So if you want to kind of think of a generalized statement where you're trying it in multiplying everything in the group of units of z mod nz, such a statement doesn't necessarily hold in general, because you could have multiple roots. And so, yeah, that's kind of what I want to talk about.